think we can still, we're still sharing. All right. So last time we were talking about bromination, and we were, this is one example of halogenation of alkenes. You can do this reaction with chlorine with exactly the same stereo selectivity. The reaction involves formation of a bridged bromonium ion, like we talked about, a three-membered ring that's bonded to carbons 1 and 2 at the same time, and then that three-membered ring gets opened up by the other bromide, the one that left when the olefin attacked the bromine sigma star, and it attacks from the backside, as typical for SN2 reactions, and you get inversion of configuration. So in the way we've drawn it, bromine leaves from carbon 2, the new bromine comes in from the bottom on carbon 2, and that's why bromine is up on carbon 1 and Br is down on carbon 2. Of course, in this case, carbons 1 and 2 are identical, so bromine could just as easily have attacked carbon 1, and that's where we get the other enantiomer from. We talked about how this was an anti-diastereomer because it was easy to see that the bromines were on opposite sides of the original alkene. But there were some questions in office hours about what anti versus syn diastereomers mean, and I feel like it's worth clarifying. Anti and syn are like cis and trans. They are relative terms, and they're meaningless on their own. So, for example, you could ask, is that an anti-diastereomer? Relative to what? When I look at it from this perspective, it looks like if my starting alkene were this, no, that isn't an anti-diastereomer. It looks like the BRs both got added to the same side. But with a little bit of carbon-carbon bond rotation, it will become clearer that this could have been the product from bromination of the trans alkene. So yes, this product is the anti-product of this, the trans alkene starting material, though it is not the anti-product from this alkene starting material. Does that make sense? So you can't call a bromination product anti or syn until you know what the alkene stereochemistry was. Let me try it out from the other direction. Let's imagine doing the halogenation reaction on this cis alkene. We would get this bridged bromonium ion as an intermediate, and then Br minus would come in as a nucleophile from the back side. Leaving group would leave. We'd end up with this stereoisomer plus the other enantiomer. Oops. But notice that through rotation around a carbon-carbon bond, I could easily make it look like this wasn't an anti-product, right? So these two stereoisomers are anti-products of this alkene. In other words, you can't know whether something's syn or anti unless you know what the starting material was. That said, the bromination reaction is itself what we call stereospecific for anti-addition. What that means is the Br goes on one side to make the bromonium ion, and then the other Br comes from the backside. So bromination can only proceed via anti-addition, which tells you that right now we don't have a way to get from the cis alkene to this product. Bromination can only give you this product from the transalkene. Similarly, we don't have a way to get to this product from the transalkene, only from the cis alkene. Right? Questions about that? That's kind of important, and there's a lot of, I feel like Emperor's New Groove Kronk, this is kind of important. If you haven't seen that, you need to do yourself a favor and go watch that. Amber and I saw that when we were dating, and it became the video we would watch like every other day in our first couple of years of marriage. Every time I got a haircut, to save money, Amber was giving me haircuts, and we would watch The Emperor's New Groove. We could now quote it all the time. One of my proudest father moments was when we were sitting around the dinner table, and I said, do I smell something burning? And young Nathan said, my spinach puffs. I was like, yes. And then Dallin, even though he was really little, would fill in lines like, a llama, he's supposed to be dead. And then he would say, yeah, wheeled, which was great. So anyway, that has nothing to do with this chemistry at all. Okay. So there's a lot of different ways to ask these kinds of stereochemical questions. You can do this same kind of thing with epoxide opening. So just as an example, go ahead and convince yourselves that the products of opening the epoxide from this kind of epoxide with OH minus are different than the products of opening this epoxide with OH minus. Right? If we open up this one, we get this set of enantiomers. If we open up the epoxide on the bottom, we get this product, which is actually the meso product. I realize I drew that fast. So be able to deal with those stereochemical issues. Another thing that is going to be useful to you as you try to keep track of these increasing number of reactions is to look for structural patterns in the products. One pattern of the product of a bromination reaction is having bromo groups on adjacent carbons. We call this a 1,2 dibromide or a vicinal dibromide. Vicinal means neighboring. And if you see bromo groups on two adjacent carbons, your mind should start to make the connection, oh, I could have got that from a bromination reaction of an alkene. Your life will be a lot easier if you work until you get to the point where where you can make that connection. Similarly, the pattern here of epoxide opening with OH minus is you get a 1,2 diol, or a vicinal diol would be another way of saying it. So if you see OH groups on adjacent carbons, you can think, I could have got that from opening up of an epoxide with OH minus. We haven't yet showed you how to get an epoxide. We'll do the easiest and most reliable way to do that. We won't learn until chapter 12, though in just a couple minutes we're going to make a molecule that can be converted into an epoxide. All right, other questions so far? Yeah?
Did you draw the mechanism of the OH?
Yep. the mechanism of OH attacking the epoxide is exactly the same as the mechanism of the nucleophile attacking the Br minus. It attacks from the backside. You get an intermediate, which I can draw where the oxygen that left would be negatively charged, and then that would need to pick up a proton from the solvent, which is probably water. Okay, others? All right, so the fourth reaction in chapter 10 may be presented as a separate reaction in the text, but it's actually exactly the same as the bromination reaction. The only difference is what is the nucleophile in the second step. Your text calls this halohydrin formation. What is a halohydrin? A halohydrin is a molecule that you get, is a molecule that has an OH on one carbon and a halide on the other. As an example, you can take this starting material. You can use bromination in the presence of water. You're going to use water as solvent, which means it is in exceedingly vast excess. So, as before, you're going to get a bromonium ion intermediate, but instead of Br minus being the nucleophile in the second step, you're going to have water do the attacking. And the reason water can do the attacking, water's a weak nucleophile, sure, but the bromonium ion is really reactive, right? It's not even just Br as a leaving group, it's a Br plus. So by having water attack, you not only allow Br to leave as a neutral group, but you also relieve this ring strain of the three-membered ring. So just like with opening of the bromonium ion with Br minus, this process occurs in an SN2 fashion with backside attack and inversion of configuration. So the products that we would get from this reaction would have the water and the Br on opposite sides. We would form both enantiomers, which I'm going to represent with the plus or minus in parentheses. We would get the other enantiomer from attacking of carbon B instead of carbon A. And then in a final step, water, an additional water molecule from the solvent removes a proton from the protonated oxonium ion to give you your final halohydrin product. That's the name for a product where OH is on one carbon and Br is on an adjacent carbon. And notice that the stereochemical outcome is exactly the same. You get anti-addition of Br and OH across the original double bond. Okay, other questions you want to ask here? Yeah.
Is one way that is helpful to remember anti and syn is that they're anti if one of them is up and one is down relative to the other, and syn is when they're both up or both down?
Is one way to remember anti versus syn if one is up and one is down versus whether they're both up or down. You've got to be careful with that, because if I could redraw this molecule, same exact molecule, I haven't done anything other than rotate around carbon-carbon bonds, but now it looks like they were added on the same side.
So one way to check that would be to make it the cis alkene the same as the starting materials, and then to look at the addition?
Yes, so one way to beat this little trick is to draw the carbons that were the carbons of the double bond and the two carbons that were adjacent to the double bond in the same shape as they were in the original alkene. That way you can tell that they were added to opposite sides of the original alkene. But beware, I mean, I could easily give this problem to you on a test and ask you what the starting material was, and you can bet you that one of the options is going to be that, except it's wrong, right? So you got to be able to follow the stereochemistry of the starting material all the way through to product. And yeah, the way you beat that is just draw those carbons in the same shape as they were in the original alkene.
Sure.
Yeah.
So you might have already answered this, I missed it, but how do you know if the negative Br ion, negative charge ion will attack backside or if the H2O
Right.
backside?
Yeah, so the question is, how do you know whether Br minus will do the attacking as we did for halogenation up here versus down below whether water does the attacking? You're going to do these kinds of reactions in many cases without solvent. Br minus is, Br2 is a liquid, and a lot of olefins are liquids as well, and so you can do the reaction without any solvent at all. But at least whatever you do, the solvent you use isn't going to be water or an alcohol. And that way, the only thing that can come in and attack is the Br minus. The reason you get something different here is just that water completely outcompetes Br minus in the next step. I mentioned this in the first hour, and I'm not sure it was that helpful. It may have added to the confusion. But when you do organic reactions, usually the concentration of reagents is in the range of sort of 0.1 to 0.001 molar. Whereas the concentration of water, pure water, is like 55 molar. So you're looking at least 500 times to, 50,000 times as much water as there is Br minus. And so if you have water present as the solvent, water is going to do the attacking in this second step, just by competition, just statistically. All right. Would the other Br ion stay dissociated in water? Yes. So yeah, and if you pay attention in the end, I've got Br minus from here, and then I removed a proton from my intermediate to get the neutral product. So yeah, as a byproduct of this reaction, I make H3O plus and Br minus, which is what I would get if I added HBr to water in the first place. So yeah, you would expect this reaction to make the water acidic, and probably if you want to isolate this product, you have to neutralize this acid along the way. That's a technical detail that we won't worry about though. Okay, so making the halohydrin is exactly the same as making the dibromide, only you're including water so that it does the attacking in the second step. However, the fact that carbon A and carbon B don't end up attached to the same things means that there's a potential for connectivity differences. I told you that with this intermediate, it didn't matter whether water attacked carbon A or carbon B because they're both identical. But if I use a different starting material, we've got a question as to what we're going to observe. All right, so let me show you the products of this reaction, and then let's rationalize them. Instead of using water as a solvent, let's use methanol, which if you don't like the ME abbreviation for methanol, we can use CH3OH. You're going to make the bromonium ion intermediate, and you're going to make its enantiomer. That you would get from bromine adding to the double bond from the bottom face instead of the top face. I'm not going to draw that enantiomer because I want to focus on the issues of regioselectivity. Now carbon A does not equal carbon B. So we've got a similar challenge as we had before with epoxides. So let's just review what we learned from epoxides. Which, that's kind of a terrible drawing of an epoxide. Okay, so what were what did we learn from epoxides? If you use a strong nucleophile under negative charge conditions, which of the two carbons gets the nucleophile? It's the less substituted one because the reaction is very SN2-like, so sterics matter. So yeah, your nucleophile comes in and attacks the less substituted carbon because it's easier. But if the epoxide, if you're protonating the epoxide first, we get the opposite selectivity. Do you remember why that happens? Right, it's more, we said the mechanism here is an SN1-like SN2 reaction, by which we mean that the OH group leaves a little bit from the more substituted carbon, so the more substituted carbon can have the partial positive charge. And then because that's where the partial positive charge is, the nucleophile attacks there. Is that sounding familiar? Now, it's possible that that explanation didn't make a huge amount of sense to you the first time we talked about it. So we're going to have a chance to review that now as we talk about what's going on with this bromonium ion. So if you look at the structure of that bromonium ion and you calculate it, it turns out that the bond between bromine and the more substituted carbon is actually longer than the bond between bromine and the less substituted carbon. And I'm not sure how to represent that other than to maybe exaggerate it. Saying that this bond is longer and weaker. If that bond is longer, that means that the electrons in that bond don't spend as much time around that carbon, carbon A, as they do, as is the case for carbon B. As that bond lengthens, there will be partial positive charge on that carbon. That is a more stable option than the alternative where we make the bond with the less substituted carbon longer. Okay? And the reason this option above is more stable than the option below is because more substituted carbons can better tolerate positive charge because of hyperconjugation. Right? Is that okay? What?
Could you say that again?
Huh. Could I say that again? Yes, except I forgot what I said. So let's try again. Having the bond between carbon and the bromine of the bromonium ion be longer with the more substituted carbon is better than the alternative, because having that bond be longer, that sounds messy. Belonging, I feel more belonged. I'm just confused. So if you calculate the structure of the bromonium ion, the bond between bromine and the more substituted carbon is longer. That is presumably because having this long bond creates a partial positive charge on the more substituted carbon, which can better tolerate that positive charge because of hyperconjugation. So the longer bond between bromine and A is more stable than the longer bond between bromine and B. It's better to have the partial positive charge on a more substituted carbon versus a less substituted carbon. Now, the bond is longer, but it's not completely gone. So that means the nucleophile still isn't going to come in from the top side because bromine's still blocking that face. It's going to come in from the bottom side like we saw with epoxides and like we saw with regular halogenation, we're still going to get backside attack. So when we say SN1-like, what we mean is there's a buildup of positive charge on the more substituted carbon. When we say it's SN2-like, we mean we get backside attack. So it's sort of a hybrid of these two mechanisms. And what that means is that in our product, maybe I'd better just recopy this so that we can have space for drawing the product. So in the product, we're going to form the bond with our nucleophile in the second step with the more substituted carbon. And we'll get inversion of configuration where that nucleophile came in, and then the other carbon ends up with the bromine. So this reaction is regioselective because we get this connectivity shown here and not the alternative where the oxygen would be attached to the less substituted carbon and the bromine would be here on carbon A. The other step I won't show you is removing of this proton by solvent in the final step to give you your neutral product. You can call this a halohydrin. It's a little bit different because you've got an ether here instead of an OH group. It's regioselective for having your nucleophile on the more substituted carbon. And it's stereo-specific for anti-addition. And you can tell this is an anti-product because we've drawn the product with the same orientation of carbons as they were in the alkene starting material, and the two groups we added are on opposite sides. Right? Yeah?
Why does it do backside attack with methyl oxide?
Same reason as we did backside attack. Why does it do backside attack here? Same reason as we did backside attack for water at this stage, and same reason that we did backside attack here. The only reason it's methanol here instead of water is we used methanol as our solvent and not water. Okay, what else? Okay, what can you do with halohydrins? I don't know. This kind of question is a challenging one because it makes you deal with connectivity or regioselectivity issues. In addition, it makes you deal with stereoselectivity issues. I will point out that you get both enantiomers here. The other interesting thing you can do with halohydrins is you can use them to make epoxides. So if I used bromination, heck, what if I didn't want to use bromine? What if I use chlorine? Chlorine's a gas, so you'd be kind of silly to try to do this, but let's go for it. You make this chlorohydrin. You get this for making the bridged chloronium ion and then opening it up with water like we've shown you above. There's the chloronium ion. Then if you add a base, and typically the base of choice is sodium hydride. Sodium and hydride don't do a good job of dissociating into organic solvent. In fact, they're sort of insoluble and sit at the bottom of the flask in a chunk, and only the surface atoms react. So you can think of sodium hydride as ironically it's probably an improper use of the term ironically, unexpectedly a very, very sterically hindered base. It won't act as a nucleophile. It will remove the most acidic proton in the molecule, which is the one on the oxygen. Once you do that, you have a great nucleophile in the same molecule as you have a leaving group. And at that stage, you can do an intramolecular SN2 type reaction where you form a new oxygen-carbon bond by attacking the carbon-chlorine sigma star. And that will snap closed to give you the epoxide and the leaving group left. So that's one way you can actually make an epoxide. We'll learn an easier way in chapter 12. All right. So let's sort of look at the reactions that we've done so far. We did hydrohalogenation, which was adding HBr. We learned that this reaction goes through a carbocationic intermediate. We learned that the reaction is regioselective to having the Br end up on the more substituted carbon. In this example that I've given you, there isn't a more substituted carbon, but similarly, if you did alkene hydration with catalytic acid with water, you're going to get the product where the OH is on the more substituted carbon. It also goes through a carbocationic intermediate. So we would say these two reactions have what we've talked about as Markovnikov regioselectivity, but they are not stereospecific, meaning you can get both syn and anti products because you go through the carbocationic intermediate. The third reaction was halogenation, which we just did above. There is no carbocationic intermediate. It is selective for anti-addition. There are no regioselectivity issues to deal with because both of the carbons in the double bond end up bonded to bromine. So it doesn't matter who forms which bond first. You can't tell. But if we do halohydrin formation, as we've just discussed, you're going to end up with the Br on the less substituted carbon and the OH on the more substituted carbon. So here again you see what we would call Markovnikov regioselectivity, and we see stereospecific for anti-addition. So that's what we've done so far. What we haven't seen an example of yet is where a nucleophile ends up on the less substituted carbon. We haven't seen an example where the nucleophile ends up on the less substituted carbon. And we've also not seen an example of a syn addition where the two things get added from the same side of the double bond. So now the last reaction from this chapter is going to satisfy both of those things. We're going to get anti-Markovnikov regioselectivity, meaning we're actually going to put OH on the less substituted carbon. And second, it's going to be a syn addition. All right, so this reaction is called, and it's reaction number 5, hydroboration oxidation. It's a two-step reaction sequence. And the effect is to do alkene hydration. You add water across a double bond, but you get the proton on the more substituted carbon and the OH group on the less substituted carbon. So let me show you an example of this reaction. This will demonstrate the regioselectivity issue. The first step of the reaction is to use a molecule called borane. Boron is just before carbon on the periodic table. When neutral, it is only bonded to 3 things. borane is an electrophile. The empty orbital that can accept electrons is the p orbital on boron. And in the first step of this reaction, our nucleophile is the alkene, and the relevant orbital is the carbon-carbon pi orbital. And so the first step of this reaction is HOMO attacks LUMO. Pi bond attacks empty p orbital on boron. Okay? So you might be tempted to draw the mechanism this way. Of my two carbons, A versus B, which do you think should get the new bond to boron? Suppose we make a new bond and we're going to have one of these atoms is going to get a bond to boron and the other is going to get a positive charge. Who should get the positive charge? Go ahead. A, because it's more stable there, right? So you might be tempted to draw the mechanism like this. And boron now is bonded to 4 different things, and so it would have a negative formal charge. Now, there's actually evidence that this is not all that happens in the first step. That is, there's not a lot of good evidence for a carbocationic intermediate. But I wanted to show you this potential intermediate so you could get the idea that we want to form the new bond with the less substituted carbon so that the carbon that is electron deficient is the more substituted one. In reality, what happens we don't observe this intermediate. In reality, the reaction is concerted and gives us the following product directly. So it's like, it looks like we never formed this intermediate, but it almost looks like we took hydrogen with its electrons and we installed them on that more substituted carbon. All of that appears to happen in the same concerted step. So if I were to draw a transition state for this reaction, we'll be looking at the alkene from the side. Here's that more substituted carbon A, and here's less substituted carbon B. As the reaction happens, the pi bond is going to break, and it's going to break in such a way that the electrons are more towards carbon B, and there's a buildup of positive charge on carbon B. At the same time, we're making a new bond between boron and carbon. And it looks like at the same time the boron-hydrogen bond is weakening and getting longer. One thing to know about boron and hydrogen is that boron is less electronegative than hydrogen. So if this intermediate that we proposed earlier that's not observed, we would have said that this negative charge on the boron would actually be out mostly on the hydrogen. So it's not too much of a stretch to believe that as we form a new carbon-boron bond, some of the electron density from the boron-hydrogen bond ends up mostly out on the hydrogen. And that's exactly where it should be because it can line up with the positive charge, the developing positive charge on the carbon. The way we would draw this mechanism in a single step would be simply to have alkene electrons attack the boron, and then hydrogen leaves with these electrons and they attack the more substituted carbon. All right, So that, the hydroboration oxidation step gets us to this intermediate where we have the hydrogen on the more substituted carbon and the BH2 on the less substituted carbon. Then in a second step, you do the oxidation, and that's adding peroxide under basic conditions. I won't show you the mechanism of that step because though it's fairly straightforward, it's details that actually don't really matter. And so the effect of this oxidation step is to replace the carbon-boron bond with a carbon-oxygen bond. And you can think of that as magic Lego chemistry if you want. As I said, the mechanism is known, but I don't care that you know it. Now that's the regioselectivity of this reaction that we've talked about. You end up with the OH on the less substituted carbon. Contrast that product with what you would get from the same starting material under acidic conditions, where because of the carbocationic intermediate, you would end up with the OH on the more substituted carbon. So we can go either way now. We've got two options for regioselectivity. We can, under acidic conditions, put the OH on the more substituted carbon, or using hydroboration oxidation, we can put it on the less substituted carbon. And then the last thing we need to do for this reaction is just to demonstrate the stereospecificity for Syn addition. Because this reaction is concerted, it happens at the same time. Boron gets attacked from the same face that the hydrogen gets delivered to, because this bond is too short to span both sides of the alkene. So that if we did the hydroboration step on this intermediate, or on this starting material, the hydrogen's going to end up on the more substituted carbon. The boron will end up on the less substituted carbon, but they're going to be on the same side, and that's Syn addition. I guess I'll point out that this product is chiral, so we would get both enantiomers, and then I will do the oxidation step where we replace that carbon-boron bond with a new carbon-oxygen bond. Notice that we do not change stereochemistry at carbon B when we make that replacement. It's not an SN2 reaction, it's something different. You don't need to know it, but its effect is to replace BH2 with the OH without changing the configuration of that stereocenter. All right, questions? Yeah.
If we were just gonna go through and make some flashcards like you recommended, would this be a good lecture to look at? Just like we listed all the different reactions learned up to this point.
So if you were to make some flashcards, okay, I got the if, I didn't get the question. Sorry, Stan.
Yeah, no, you're all good. Basically, like, what's the place we can look to that's the most comprehensive, showing all the reactions that we should
Oh,
kind of
okay.
take to be able to recognize products, reactants?
Okay, so if you want a place that summarizes the reactions for this chapter, usually the end of chapter will have a summary of the reactions. I've got some handouts from previous courses, chapters 9 and 10, that summarize the reactions. I could make them available to you, though I'd need to check them first because I always tweak what I expect people to know, and there may be some out-of-date material on them. So I'll take a look at that and try to make them available. But I don't think there should be really any surprises. If you consult the text or the study guide, it should have everything you need to know. Okay, others?
Just a couple of questions.
Yeah, there's a question about what's the difference between acidic and basic conditions, and I'm not sure I understand the question. I think what I was trying to illustrate was if you use hydroboration and oxidation, you get the OH on the less substituted carbon of your original alkene. In other words, OH ends up on carbon A. If you do the reaction under acidic conditions, the mechanism is what we would get from last time, where we remove a proton from the acid to get a carbocationic intermediate. You make the new bond with hydrogen such that the positive charge can be on the more substituted carbon where it's more stable, and that's where the nucleophile comes in and attacks. So another question is the Chapter 10 study guide still going to be due on Saturday? So I wasn't even really aware or paying attention. I know that it was on the calendar that Friday is apparently your token spring break day. You'll take it, but, you know, whoop-de-doo, right? Yes, so we will not have class on Friday, but we will have class on Monday, and we'll make the Chapter 10 study guide due on Monday or Tuesday. Let's see, and then Joe, there was a question about why, for this reaction, why just from the top side? The key issue here is that BH2 and the hydrogen need to be on the same side. You would also get the other enantiomer. I was just in a hurry and didn't want to draw it, but I can. And it looks like this. And while I finish drawing that, I will bid you all a fond farewell until next Monday. May your spring day be springy.
Hey, Dr. Prince, could I just clarify my question that you drew out right there?
Sure.
So I think I'm more wondering why the H and BH2 have to be on the same side. Is that
Okay.
just a mechanism we don't have to know? Or?
No, it is something I want you to know, and it's because of this transition state. As you form we're looking at this alkene sort of on the side. I could even, if you want, draw the plane that the alkene's sitting in. As we form the new carbon-boron bond, and then the hydrogen gets delivered, these atoms
Since they're both coming in
from the same side, yeah. There's not enough space or distance in any of these bonds to allow the boron and the hydrogen to stretch to opposite sides.
Okay, yeah, that totally makes sense. Thanks so much.
Okay, you bet. Partial negative on the hydrogen because hydrogen's more electronegative than boron.
Affects the, instead of 10.
You bet.
Thanks, Dr. Price.
Yep. Not hugely so, but enough to make a difference.